Alright, this is our project. It's a flyback converter, and over here we can see the waveforms. The green is current, the yellow is output voltage. As you can see, it's at 44 volts for a 20 volt input. We have 100 kilohertz PWM going into the gauge driver. The MOSFET's underneath this heatsink right over here, and you can see the blue waveform on this screen is the PWM. This is the voltage sensor voltage, and as you can see, as we vary the voltage, it goes down, corresponding to the sensor gain factor. Over here is the load of 50 ohms. This is our flyback transformer and current probe. So we're at 0 volts right now. As you can see, this is the starting duty cycle on the oscilloscope. We have 0 volts on our output. Alright, we're gonna slightly start increasing the voltage until we reach the value of control. Alright, there we go. As you can see, the control scheme is altering the duty cycle slightly to maintain the output voltage at roughly 11 volts. So being a flyback converter with roughly the output should be typically in open loop 2 times the input voltage. Right here we have 8, so we expected the output voltage in open loop to be around 16 volts. However, it's maintained at 11 volts, and as you can see, the output right here on the oscilloscope is shown as 11 volts. Even when we move around the input voltage to about even to 9 volts, to give you almost a 1-to-1 ratio, we're still maintaining about 11.9 volts on the output. And furthermore, as we decrease the voltage, you can see the duty cycle increase to try to maintain that output voltage of 11 volts, but of course after a certain limit it falls. So we're at 0, we're going to start increasing it, and we have the code set up to trigger at around 25 volts on the output in order to begin its control scheme. However, over here you're kind of going to see the limits of our control scheme and setup because it's going to get very noisy. However, within that noise, you can see the output voltage right now is 34 volts. And you can see that's only off a 16 volt input. We can increase the voltage very slightly. We can even increase it to almost 20 volts, and it's going to maintain 34 volts. So as you can see right there, we have a maintaining at 34 volts even at a 20 volt input. If I can kind of take a look at these waveforms and try to reduce the noise, it's going to be kind of very difficult. Let's do a run stop here. Okay, there we go. You could see the duty cycle has been slightly adjusted. I don't know if you could tell through the noise, but the control loop is adjusting the duty cycle again to maintain 34 volts on the output. So we can, I can go and see if we can reduce this voltage right here. So as you can see, I'm reducing it 17 volts, and we're still maintaining 34 volts on the output. Again, 15 volts, still maintaining 34 volts. So throughout that range, even though it's kind of limited, again, with all the sensor noise that we're facing and all the issues we're facing, we're still able to do a decent control loop, even at 22 volts right now, again, maintaining 34 volts. And I'm just going to go ahead and do one more time, reducing the voltage. As you can see, we have it going down to 15 volts, again maintaining about 34 volts. So there it is. So some of the problems we face right here is that this is our DSP, or microcontroller as you would say, that we've using the computer right here in Code Composer to upload code. Some of the issues we're facing is that the output, PWM output of this microcontroller is only 3.3 volts, and the gate driver for the MOSFET takes about at least 5 volt input to be able to fire properly. So to compensate for that, we've had an op amp with the appropriate gain to give about 7 or 8 volts PWM output to the gate driver. However, with all those wiring over here going around. There's a lot of noise, which adds some difficulty in controlling the output.